Okay, yeah. So welcome back, students. So I welcome you all to this 9th lecture on this Abhyas series of fluid mechanics, basically on this potential flow. So am I audible? So please confirm. Am I audible to all of you? So please confirm, students. So please type in the chat box, am I audible to all of you? Yes, audible. Great. So this is basically the lecture on this concept of potential flows, which is one of the most important chapters actually in fluid mechanics, of course. And if you see, whatever the flows we see, basically the vortex flows, linear flows, all these flows can be covered in this single chapter, potential flows actually. Okay, so this is such a very good topic in fluid mechanics. Okay, and of course I'll teach you this fluid potential flows in a slight different approach using complex numbers, which some of you might not have heard before. So today's class basically straight away going to questions. Before that, I'll give you some basic concepts of potential flows actually, some for 15 to 20 minutes, and then we will start the session. Okay, so is this clear to all of you? So please type in the chat box, because many of you might have seen some lengthy expressions in potential flows and all, but in today's session we will deal it in a short way using complex numbers. Okay, so that's the way how we teach potential flows actually, and this is the last individual lecture on chapters, and tomorrow we have a comprehensive, means basically the total we'll talk about the questions on complete fluid mechanics actually. Okay, so that's how we'll come to a conclusion to this Abhyas series basically. Okay, and yes, this topic is very important for civil engineering, and also if you have a mechanical and other things, this topic is there in XC. Okay, so in engineering sciences paper in fluid mechanics you have this potential flows. Okay, so without any delay, let us start some discussion on this potential flow actually, and then we'll solve for questions. Okay, some just 15 to 20 minutes of introduction quickly. Okay, quick introduction. So basically potential flow, potential flows. So normally this potential flows is known with some another name, which are called the ideal flows actually. Okay, so these are ideal flows. Okay, so ideal flows, what do I mean by this? Ideal is generally incompressible, inviscid means you don't have any viscosity in the picture. Okay, so you are not going to consider any viscous effects that comes into the flow, and also irrotational flows basically. Okay, so these are irrotational flows. What's the meaning of this irrotational flows? You always have a velocity potential function existing for these flows. Okay, so always there exists some phi. Now if you see, for example, let us suppose you take a velocity vector v bar is equal to u plus ui plus vj, for example. Okay, if you take this velocity vector ui plus vj, for example, then in that case normally this is some function of x comma y. Normally if I take the 2D case, this v is also some function of x comma y in general. Okay, so now if this is the velocity profile, for example, now if you want to convert this velocity profile into some polar coordinates, for example, okay, so how you can convert? I'll just show you how you can convert this. Okay, I won't do the derivation right now because it's a short course, so but I'll give you the results what comes out. Okay, so let us suppose if this is your x-axis and if this is your y-axis, for example. Okay, so x and y. Now let us suppose you have some velocity vector, for example, something like this. If this is the velocity vector for you, okay, if this is the velocity vector, then if you take projections of this, then obviously you have, if you take the projections of this, you have this y component of velocity, which is v, this y component of velocity, which is v, and at the same time you also have the x component of velocity, which is u. Correct, so you have these projections u and v. Basically if this is your velocity v bar, for example, if you take the projections on x component and y component, you have u and v. Now let us suppose if you want to take the same projections in polar coordinates, means let us suppose you have some radial and, for example, radial and azimuthal velocities, for example, like this. Okay, so let us suppose you have certain let me shorten this a while. Okay, so let us suppose if I want to write this as u r and u theta, for example. Okay, these two are again perpendicular to each other. So this is the radial component of this, and this is the azimuthal component. If you write it in radial and polar coordinates, then the same the components u will be in terms of ur and u theta. The component v will be in terms of ur and u theta. Okay, and if you take the expressions for that, you have small u is equal to ur cos theta minus u theta sin theta, and v is equal to ur sin theta plus u theta cos theta. Okay, so this is how you actually get the components. Of course, you need to use little geometry and trigonometry here, purely mathematical. Okay, just if you take the projections, triangles and all, you will get. Okay, but right now I'm not doing it because it's a short course. So u and v, yeah, basically denoted with this ur and u theta components. Okay, now what we actually do is, how you can write this u and v, for example. So we define something in complex numbers. You might have learned this in mathematics in complex functions. There is something called analytic function. Okay, so what is an analytic function? Basically, at any given point its derivative exists. Means similarly in a flow, for example, let us suppose if you have a flow, for example, two-dimensional flow. So in that two-dimensional flow, at every location the flow has certain velocity vector. This is what the meaning of analytic in fluid mechanics. Okay, so now if you see, if you define some function f of z, this function is called complex potential. Complex potential function, which is basically equal to stream function, this velocity potential function plus I times of stream function actually. Okay, so this phi of x comma y is nothing but your velocity potential function, velocity potential function, which you generally see for any rotational flow, and this psi of x comma y is the stream function. Okay, so this is your stream function. Now you define this complex potential function, and we say that at every location in the flow this function basically has its differentiation. Means this function is continuous at every point, and of course it has its derivative. Okay, now let us see, if you differentiate it partially with respect to x, for example, let us see what happens. Okay, so you know f of z is equal to phi of x comma y plus I times of psi of x comma y. Okay, now try to understand this. Try to understand carefully here. If I keep differentiation of this f dash of z into inner differentiation of z with respect to x, how much is the inner differentiation? You know, z is equal to x plus iy. So if you differentiate this with respect to x partially, then what we will get? If you differentiate it with respect to z partially, we will get dz by dx is equal to, or dz is equal to dx. Okay, plus I into dy, and of course if you are doing it partially, then you know dou z is equal to dou x, and this will be 0 in that case. Okay, so differentiation will be same. So this is equal to dou phi by dou x times plus I times of dou psi by dou y, dou x here. Okay, you are differentiating this partially. I is a constant value. Okay, so since please, civil engineering or not? Yes, civil engineering. Okay, it is there in the syllabus of civil. So see here, f dash of z can be written as like this if you differentiate this partially with respect to x. Now you know, when you define the concepts of velocity potential and stream functions, you know that the velocity potential is in such a way that if you take the gradient of this velocity potential function, you will get v. What is the meaning of this? Dou phi by dou x I bar plus dou phi by dou y j is equal to u I plus vj. This is the velocity vector. So if you compare, you know, u is equal to dou phi by dou x. So this can be written as u means for any velocity profile, v bar is equal to u plus iv. This first term can be written as u plus I times of, now, stream function. So what is the relation between velocity potential function and stream function? You know, these two functions, they satisfy the Cauchy-Riemann equations, correct? So what are Cauchy-Riemann equations in complex calculus? If you have f of z is equal to u plus iv, for example, okay, okay, let us take, for example, phi plus I times of psi. Let us suppose you have this velocity potential and stream function. Now the Cauchy-Riemann equations are dou phi by dou x is equal to dou psi by dou y, and dou phi by dou y is equal to minus dou psi by dou x actually here, correct? So these are the Cauchy-Riemann equations. Yeah, good morning all of you. So these are the Cauchy-Riemann equations, and if these Cauchy-Riemann equations are satisfied, then I can replace this dou phi by dou x with minus of dou phi by dou y. Okay, so minus of dou phi by dou y is nothing but minus v. So that's how at any point in the field, in the flow field, you have this f dash of z is equal to u minus I times of v actually here. Okay, so this is how you get the complex function. Means basically you have a flow. For example, let us suppose if there is some flow which is moving in the at some random direction, say alpha for example. Okay, if this flow is moving at some random direction alpha for example, in this case, now you know the magnitude of this flow is v, then you know the x component of the flow, means the x velocity, x coordinate of the flow and y coordinate of the flow, correct? Y coordinate of the flow velocity. So what are the components? You have v cos alpha and here you have v sin alpha for example. Okay, so now you know that u for this flow condition is v cos alpha, u is equal to v cos alpha and v is equal to v sin alpha for example. Okay, v is equal to v sin alpha in that case. Okay, this v and this v are not same. Okay, these are just projection values. Now if you see, if you replace here, you will get f dash of z is equal to, means for that particular flow condition, let us suppose you have some flow at some velocity v at an angle alpha, then in that case we have v cos alpha minus I times of v sin alpha is what you have actually. So this can be written as cos alpha minus I sin alpha can be written as e to the power minus I alpha. This is again some constant. Okay, e power minus I alpha is constant. So that's how, if you see carefully here, we generate this f dash of z function. So once you have this f dash of z, you can calculate f of z. So that's how, depending on any flow, basically let us suppose if you have some linear flow, vortex flows or source sink flows, whatever might be the case, you always know this velocity. So once you know this velocity, you define this function, and if you do the integration, because if you know f dash of z, then if you want f of z, you need to go for integration. That's it. Okay, and how you will integrate? We integrate with the help of Milne-Thomson method, which is very much known in complex calculus. Basically for integrating complex functions, you have this Milne-Thomson method. Okay, so if this is the case, then if you integrate, for example in this case, f of z will be equal to v into e power minus I alpha. This is completely constant because this v is having some uniform magnitude in that case, into z. So this is how we get the complex potential function for this type of flows. Okay, similarly I'll give you complex functions for various flows. Okay, for vortex flows, source, strength, everything I'll give you. Okay, now let us see one thing. For example, we came to know that f dash of z is equal to u minus iv. If you convert this to polar coordinates, for example, you will get something like this: ur minus I times of u theta into e to the power minus I theta. Okay, just you replace u is equal to this value, and v is equal to this value, and if you make slight modifications, slight adjustment of the terms, mathematical simplification will give you this thing. So this is how you write f dash of z in Cartesian coordinates, and this is how you write in polar coordinates. So for Cartesian I have seen you. Now let us suppose what are the velocity potential functions. Okay, so basically, so this is in mechanical syllabus, not in purely mechanical, but this is in XC syllabus. Okay, so that's why I'm taking this. So f dash of z is equal to ur minus I times of u theta into e to the power minus I theta. This is what you have actually. Okay, now if you see this Cartesian and polar coordinates, now for any flow that you take, we can generate this f dash of z easily from these two expressions, and once you find f dash of z, you can go for the calculation of f of z. Okay, just by integration. And how you do the integration of Milne-Thomson method? Look, I'll help you out. Okay, so for example, let us suppose you have some velocity potential function. Then if some velocity potential function is given, how to find the stream functions we will see. Okay, because generally in potential flows, normally in fluid mechanics, it's quite obvious that they sometimes give you velocity potential functions and they'll ask you for the stream functions. Okay, or they'll give you stream functions and they'll ask you for the velocity potential functions. If you remember in your mathematics, in complex calculus, you might have observed this. They'll ask you if f of z is analytic, u is equal to some function, then what is v? They'll ask you this type of questions. Correct? You remember, they'll give you f of z is equal to u plus iv is analytic, u is given by some function of x comma y. They'll ask you what is v. Have you done these type of questions anywhere? One of the most important type of questions in complex calculus for university exams actually. So please type in the chat box, have you ever seen this kind of questions? So here this is very much similar to giving you the velocity potential function and asking you for the stream function actually. Clear? Or sometimes if they give v, then they'll ask you for u, which means if they give you stream functions, then they'll ask you for the velocity potential functions. Okay, so we will know if one of them is given, how to calculate the another. Okay, and now one very important thing, for example, let us suppose you have this. For example, let us suppose I am taking vertex flows. Okay, vertex flow, for example. Okay, I am taking vertex flow. Let us see how we can generate a vertex flow. For example, I am talking about one of the flows, which is vertex flow. You know, vertex flow can be betterly analyzed in polar coordinates, so let us use polar coordinates. Vertex flow. Okay, so let us suppose you have some vertex flow. Now if you want to generate a vertex flow, x and y axis, for example, let us suppose this is x and this is y, x and y here, minus x and minus y. So this is basically a plane. Okay, plane vertex. We are talking about some plane vertex. Now you know how vertex flow actually looks, something like this. So same cycle again. Okay, so basically this is how you have the vertexes, correct? This is how you have the vertexes. Now in this vertexes, at any location r, for example, if you take, the flow will be only in this direction, correct? The flow will be, means if you take any particle on this radius, this particle will not have any radial velocity. It just tries to rotate, or it just tries to revolve about this axis, correct? If you take a perpendicular axis like this, at any point in the flow, the particle will just try to revolve about this circle. Okay, now in that case, if you see carefully, at any point in the flow, if you take, the particle has only velocity in the theta direction, correct? U theta is not equal to 0, of course, and you know the particle doesn't shift from one radius to another radius, so u r, the radial velocity of the particle, is 0. We know this, correct? We know that u theta is not equal to 0 and u r is equal to 0, for example. Now let us see, we know from free vertexes, let us suppose if you are talking about free vertex, if you are talking about a free vertex, then u theta is equal to some constant divided by small r. This is how the velocity profile comes out, correct? We have seen in case of a free vertex, v theta is actually equal to c divided by small r. Okay, now if you replace here, we have f dash of z for plane vertex. Let us suppose I am writing for vertex flow, for vertex flow, for vertex flow. Let us see, we know u r is equal to 0 and u theta is equal to c by small r. Okay, you know this much, u theta is equal to c by r. Normally for any vertex flows, this is the case. So if you write this complex potential differentiation, f dash of z, this is equal to 0 minus I times of c by small r into e power minus I theta. This is what you actually have, correct? So this is what actually you have. Now you know this can be written as minus c by r into e power I theta, correct? So you know this is c into this e power minus I theta can be written as e power I theta here. So if this can be written as e power I theta, you know this complex number z is equal to x plus iy can be written as r into e power I theta in modulus amplitude form, correct? So if you see, we can write the complex number at any point as x plus iy, or we can also write as small r into e power I theta, where small r is the distance of the point from the horizon and theta is the orientation of this line. Means for example, if I take this line, if I am talking about this point, then you know this is theta basically and this length is r, so we can write that. So this small r can into capital R, small r into e power I theta can be replaced as z. So this is minus I times of cz is what you have here. Okay, so if you f dash of z is minus I c by z, then f of z is nothing but minus I, c is constant, integration of 1 by z is ln z. That's it. This is the complex potential function that denotes the vertex flows. Okay, so basically you have observed why I have given you these two expressions, but right now I haven't derived them because it will derive that somewhere in some comprehensive course if I take some time. But f of z can be written by this complex potential functions actually. Okay, and you all know how to write the log z function, for example, correct? So log z function is known to you. So if you know how to write the log z function, log z can be written as log r into e power I theta. So this is log a into b form, log a plus log b, log b. So you know ln r plus this value ln x power something can be written as this something into ln e. And you know, this value of natural logarithm of e is 1. So ln r, if you take ln r, what is ln r basically here? Ln root of x square plus y square plus I into theta value is tan inverse of y by x, correct? Because if you see from this polar amplitude form, if you have a axis like this, x, y. Now let us suppose if you have a line from this point over here, okay, so r and theta value, okay. Now if this coordinates are x comma y, then you know this length is y and this length is x. So small r is equal to, from Pythagoras theorem, root of x square plus y square, and tan theta is equal to y by x. So theta is equal to tan inverse of y by x, okay. So since this log z has to be multiplied with this minus ic, so if you multiply this with minus ic, this implies minus ic ln z is equal to minus ic ln root of x square plus y square plus I into minus ic. I into I is I square is minus 1. There is one more minus. So c into tan inverse of y by x. So if you observe carefully here, this is the complex potential function, and I told you one very important thing, that f of z is nothing but velocity potential function plus I times of stream function, correct? I have given you this, which means if you observe carefully here, these functions phi of x comma y are denotes the velocity potential function. This function c times of tan inverse y by x, this denotes the stream function actually here, okay. And you know, velocity potential function and stream function, these two will be orthogonal to each other, means they are actually perpendicular to each other. So in that case, if you want to draw equipotential lines, let us see how equipotential lines look like, okay. Okay, I think I have put some questions, just a minute, we'll take some more slides. Okay, so fine. Okay, so see here how we can write that. So phi of x comma y, phi of x comma y is equal to, phi of x comma y is equal to minus c times of, this is phi of x comma y, right? If you multiply minus I c ln z actually here. So for this vertex flows, this is phi of x comma y, because this is the L part and this is the imaginary part. So this is phi of x comma y, and psi of x comma y is like this, okay. So now if you see carefully here, this is phi of x comma y and this is psi of x comma y, because this is the imaginary part, I is here, okay. Psi is the imaginary part of this function, so psi value is this. Now if you take phi values, phi is nothing but tan inverse, okay, c times of tan inverse y by x is there, okay. So these are the phi values. Now if you see carefully here, c into tan inverse of y by x, correct? This is phi, yes, phi of x comma y is equal to c times of tan inverse of y by x. Now if you want to draw equipotential lines, for example, okay, so if you want to draw equipotential lines, you can see, if you make this is equal to some constant c1, then this constant c by c1 is one more constant. So tan inverse of y by x is equal to some constant, let us say k for example, then y by x is equal to tan inverse of this constant is actually one more constant, k dash for example, if you see. So this equipotential lines are of the form y is equal to some constant into x. So this means this k dash is arbitrary constant, you can keep any values. So that means this equipotential lines are nothing but straight lines passing through origin, straight lines passing through origin, straight lines passing through origin, okay. Now if this is the case, then let us see what are streamlines. Psi of x comma y is equal to, psi of x comma y is equal to this quantity minus c times of ln root of x square plus y square. So minus c times of ln root of x square plus y square is equal to some constant, arbitrary constant. So if you delete this minus sign c and all, again we can get ln of root x square plus y square is equal to some constant c2, correct? Now if you see, if you take exponential on both sides, e power log of this quantity is equal to e power c2. E power c2 is again some constant, so root of x square plus y square is equal to some constant k, and x square plus y square is equal to some constant k dash. Let us say this k dash can be written as root k dash whole square, for example. Okay, so now in this case, if you see, if you change the value of k, you will get different circles, but all these circles are concentric circles. They have the same center. So these are concentric circles which are having center at origin. You know this much. Okay, so means for vertex flows, if you understand it using simple complex numbers, we haven't done big derivation, we have just done 2-3 steps. Then after, this is mathematics I have done, log z value I have shown you. So if you compare this velocity potential functions and stream functions, now you can clearly see the stream functions are nothing but concentric circles. Okay, and obviously, you know, in this vertex flows, if you see, these circles are nothing but the stream functions. For example, this is psi is equal to constant 1, psi is equal to constant 1. Okay, this is psi is equal to some constant 6, psi is equal to some constant 5, all these things. Okay, now you know one thing, from your fluid mechanics point of view, there cannot be any flow across the streamlines. Correct? Means if there are two streamlines, then flow can flow in, I mean the fluid can flow only in between the streamlines. It cannot cut the streamlines. Now can you see in this vertex flows, is there any point that the point which is on one cycle will go to another cycle by cutting that streamline? Can you see this? No, you cannot see this. Okay, so these all circles basically are nothing but stream functions for this flow. And at the same time, if you see the lines passing through origin, basically like this, the lines passing through origin, these lines are nothing but your equipotential lines actually. Okay, these lines are equipotential lines basically you have, and you know, at any point radius, at this point the velocity is tangential, so these two lines are actually perpendicular to each other. You know, a radius and the tangent to the cycle, basically they intersect perpendicularly. So that's why if you see, this streamlines and velocity potential lines are very much can be calculated by using this simple analysis of this complete vertex flows is got derived in almost a one slide kind of thing. So if you see, this complex potential function makes you calculate stream functions and also velocity potential functions. Clear? You can define this complex functions for any flow in general, for whatever the flow that exists, you can always define the case. Okay, now let us see one thing. I will give you some standard velocity potential functions, okay, which you can write very helpfully. So for a uniform flow inclined at an angle alpha, inclined at an angle alpha is given by, inclined at an angle alpha is given by f of z. The complex potential function for this case is e to the power of v times of e to the power minus I alpha times z. This is the complex potential. So if you convert this into, if you write this z as x plus iy, then you will have v into x into e power minus I alpha is the stream function, is the velocity potential function, plus I into vz into minus n alpha. That's the stream function basically here. Okay, similarly for a vertex flow, this is given by f of z is equal to minus I times of constant into ln z actually here. Okay, now basically there is something called superposition of flows, for example. Okay, and before going for that, I would like to give you one more case. A source of strength m, for example. Okay, if you take a source of strength m actually. Okay, so what is the source of strength m? Means basically source is some point from where the fluid, so I use Cartesian coordinates. Yes, of course I'm using Cartesian coordinates, but these are complex numbers, that's it. Okay, we'll write z is equal to x plus iy only. Okay, we'll use complex coordinates, no issues. So now if you see carefully, this is a source of strength m. So what is the meaning of a source of strength m? Means if you have a point, for example, this is called a source if there exists continuously some fluid which comes out with some discharge. Okay, so from this point there always comes out some discharge, okay, like this in all the directions. For example, in all the directions, all over the 360 degrees, you always have some flow, and the strength of this source is defined with the discharge that actually comes out of this source. Okay, so if you want to calculate the discharge, you know the flow is in a radial direction, you are, so if you take a location where the radius is capital R, small r, for example, if the radius is small r, then at every location the velocity is in radial direction, which is u times of, which is this u subscript r actually, and the flow area is nothing but, let us suppose if the cylinder or if the space is like this, perpendicular to this, then for a unit length, if you see, the flow area available for this flow is 2 pi r, which is, if this radius is r, then 2 pi r is the circumference of this multiplied with 1 unit length perpendicular to this. Okay, so 2 pi r into 1 is the flow area available, and at every point the velocity is u r. So we can write the discharge as u r into 2 pi small r. Okay, so this is the discharge that comes out. So, and obviously you can know one thing, this is the radius. So the discharge which is at this circle, if you take another circle, the same discharge will go. So as radius increases, the radial velocity will actually decrease. So u r is actually a function of c by small r in case of this source flows. Okay, so if you see carefully here, this velocity profile at this function means at every location the flow is radial. Okay, the flow is radial in this direction. Okay, so the flow is radial in this direction. So at every location, if the flow is radial, then we have this. At another location, if you take at a bigger radius, obviously this ur value decreases because the flow area increases for the same discharge. So basically in this case you have ur is equal to c by r, and of course you see no particles will rotate, so u theta is equal to 0, and f of z for this function is given by c times of ln z, and if you calculate the value of c you can get, so this is basically called the strength. So m is equal to small u r into 2 pi r. Okay, so if you calculate the value of c, basically you will end up with the result m by 2 pi into ln z actually here. Okay, so this is the complex potential function for the source flows. Okay, and this is the case if source is at origin. Okay, means normally in the 2D case, in this location, if this in this Cartesian coordinate system, if source is at this location, then this is the complex potential function. If source is at z0, for example, at some point, it could be at any point in the flow. So if source is at z0 at some point, then f of z can be written by m by 2 pi times log z minus z0 to the base e. Okay, so this is the velocity potential function for the, the complex potential function for the source flows. Okay, similarly if it's a sink, then you know the velocity direction is opposite, so you'll put a minus here. That's it, that's the only difference. Okay, if source is at origin, this is the complex potential function. If source is at some other point z0, then this is the complex potential function for that. Okay, so similarly if you take a doublet, so what is a doublet actually here? Look, a doublet is source plus sink of equal strength, placed at a very close distance, So in that case, if you see the complex potential function, I'm not doing the derivations here, okay, because it's a small course, so small lecture, so that's why I'm just giving you the functions. F of z is equal to m by pi times of z is what you actually have here. Okay, we'll derive this maybe at some time. If we find some comprehensive course or something, we will definitely see how this is coming, but right now you can see f of z is equal to m by pi z. That's it. Okay, now if you see, if phi and psi, normally if you see these two functions, velocity potential function and stream function, they actually satisfies the Laplace equation. So basically one very important property is this phi and psi, which in turn these velocities u and v, they obey the superposition principle. Means, let us suppose in a fluid medium, if I have a source and a uniform flow, then the net flow created because of the effect of these two can be understood by just adding this function to I told uniform flow and source, so this function to this function, that's it. Okay, so you can just add the two and you can get out the things. Clear? So basically this is the understanding that I'm going to give you. And if you see superposition of flows, I would like to give some standard superposition flows. So superposition of flows, superposition of flows, superposition of flows actually here. So if you take superposition of flows, normally let us suppose if you superpose a source or a doublet, for example uniform flow plus look at doublet. If you do a uniform flow plus doublet, you actually get this Rankine half body. Okay, Rankine half body. Okay, so this is what you, this is uniform flow plus source. Okay, uniform flow plus source. If you do, you will get a Rankine half body. Why it's called a Rankine half body? Okay, I'll explain you. Basically, see here, if you try to draw the streamline of at one particular value, which is m by 2, I think we have a question, they will see anyhow in detail. So if you take this xy coordinate system, for example, if you take this xy coordinate system minus x, y and minus y, then for a particular value of stream function, you will have one streamline like this. So this is how you have a streamline. Means basically after some distance, this width of the streamline remains constant actually here. Okay, so if width of the streamline gets constant, you know, practically flow cannot enter this streamline. So there is some mass of the fluid which gets located here, and there could not be any flow like this. So this can be analyzed to some situations like submarines and all, where you have a large body like this, so that the flow in this situation can be analyzed as a flow over submarines and all, basically the half bodies. You cannot see the other, on the other side, the streamline again gets connected, you cannot see this. So that's why this is generally called as Rankine half body actually here. Clear? So we have this kind of situations when you talk about uniform flow plus source, all these things. Okay, so similarly uniform flow plus vortex, uniform flow plus vortex. Okay, you can see uniform flow plus vortex. Actually in this case you will actually get some other type of flow, basically flow past cylinders or something. Uniform flow plus doublet, you can say doublet, you can say flow over a cylinder or flow past a cylinder. Flow past a cylinder is what you will generally get here. Similarly, if you have some other functions, basically you can get such kind of structures basically for a particular value of the streamline, and that's how we talk about these things as per the geometry. For example, in this case what you will get is, at one particular value of the stream function, you will get one of the streamline as a circle actually. Okay, so in that circle case, what happens, whenever you have a circle for example and no fluid can enter like that, you can assume that there is a solid cylinder here. Okay, so that's how we can connect this flow to a flow past a cylinder. Clear? So that's how we actually connect this. There are much more superpositions, but we'll talk about them in detail in some comprehensive course when we take it. Okay, so fine, so with this knowledge what we have understood now, let us try to solve some problems now. Okay, so let us try to solve some problems using this complex potentials, because if I straightly start problems and if I talk about complex functions, you may not feel that comfortable. So that's why I have given you some quick introduction for some half an hour almost. Okay, so let us try to solve this question. A two-dimensional flow field is represented by phi is equal to 2xy minus x. At the point 2 comma 1, the value of the velocity v is dash. Okay, so I've given you, so please explain coordinates of stagnation point in half body in short. Okay, I'll explain you, no issue. Okay, we'll talk about this coordinates of stagnation point, no issue. So basically stagnation point is the point where the flow velocity is 0, local velocity is 0. We will see how we can calculate the stagnation points in any flow in general. Okay, so see here. So if two-dimensional flow velocity is represented by this function, so phi is equal to 2xy minus x. Why I have given you one simple example in the beginning is, I want to show you how you can apply the complex potential functions. Okay, I understand you guys know the answer. U is equal to dou phi by dou x, v is equal to dou phi by dou y. If you calculate, you will get uv components, you substitute the points 1 comma 2. I understand, but let me help you out in case of complex numbers, so that you will get habituated whenever velocity potential is given, how to calculate the velocity values at any for any function actually. Okay, so let us see here. Phi is equal to 2xy minus x. Okay, so now if you see, okay, classical procedure, first of all, if you see dou phi by dou x, which is 2y minus 1, v is equal to dou phi by dou y, which is 2x. So at the point 2 comma 1, if you take at the point 2 comma 1, this value is 1, and at this point we have at 2 comma 1, this value is 4. Okay, so if you calculate the velocity, you will get root of u square plus v square actually here. Okay, so we'll get square root of u square plus v square, and this is basically this is how much, square root of 17, so slightly more than 4. Okay, 4.1 around. Okay, so this value will be around 4.1. Okay, but I want to show you, yes, 4.123, okay, fine, whatever, but I want to show you once phi is given, how to calculate the stream functions actually, and then how to calculate the velocities also. Okay, now see carefully here. So see carefully here, f of z, f dash of z, we have all these things. Now see carefully, phi is equal to 2xy minus x. This is what you actually have. Okay, now let us suppose if I ask you what is the stream function corresponding to this velocity potential function phi, for example. Okay, now if you calculate this, we will get f of z, f dash of z is equal to u minus iv. For example, you have this. Okay, so u is nothing but dou phi by dou x. So 2y minus 1 minus I times of v is nothing but dou phi by dou y. Okay, so v is nothing but dou phi by dou y. So if you v, this is 2x. Okay, so we have 2y minus 1 minus I times of 2x. This is what we have. Okay, so if this is the function f dash of z, now to get the complex potential function, you need to do integration as per Milne-Thomson method. Okay, so applying Milne-Thomson method, so see how you actually apply Milne-Thomson method. Applying Milne-Thomson method, applying Milne-Thomson method. Okay, so if you apply Milne-Thomson methods, now let us see what you get. In Milne-Thomson method, you replace x with z, replace x by z, and y by 0, and y by 0. This is what you actually do in case of Milne-Thomson method. Okay, so when you replace this x by z and y by 0, this gets converted to f dash of z is equal to y is equal to 0. So minus 1 minus 2i times of x. So minus of 1 plus 2i, this x has to be replaced as z. So this is the function. So if you multiply dz on both sides, f dash of z dz is equal to minus of 1 plus 2iz dz. Now if you integrate this on integration, let us see what happens. On integration, look, I am writing each and everything here, but in exam you don't write all these statements. Once you, after this first line, you will directly write this second line. Okay, you don't write all these things in between when you are solving this question in exam. Okay, so see here, on integration, what you will do is f of z is equal to minus integration of 1 z plus 2i is constant, integration of z is z square by 2. So if you see, this 2 gets cancelled, so which means you have minus z plus I times of z square. This is the velocity, this complex potential function. Now if you write in z is equal to x plus iy, and if you simplify, let us see what happens. This implies f of z is equal to minus of x plus iy plus I into x plus iy whole square, x square, plus iy whole square. Iy whole square gives you minus y square plus 2xy. So now if you separate real terms and complex terms, you see this x is a real term, so minus x. This x square minus y square is complex term, so you have 2i into xy, because it is I multiplication is also there. Okay, so x plus iy whole square is 2ixy. So I into I again gives you minus, so minus 2xy is what you have. Okay, so minus of this value minus x, this is minus x, plus I into I is minus 1, so minus 2xy. With this minus, we have a plus sign. We have a plus sign here, plus imaginary part times of minus y plus x square minus y square. So this is what you actually get here. Okay, so this is basically the stream function. Okay, so if you see, this is the real part, which is phi of x comma y, and this is the imaginary part, which is psi of x comma y actually here. Okay, so psi of x comma y, so phi of x comma y is obtained as 2xy minus x. The main advantage of this method is you can check whether your answer is correct or wrong, because if you see phi is given to you, the same phi comes out after this integration. Okay, you can check this whether your answer is correct or not, because by doing the simple integration. Look, hardly in exam you don't write these two lines, you don't write this line, you write 1, 2 and 3 to 4 lines maximum. Okay, this z substitution of z as x plus iy and simplifying gives you this. Of course, here velocity potential I have given you very simply, but let us suppose if I give you some complicated velocity potential function, that's it. It takes so much time for you to calculate stream function, which we will see one example also. Okay, so this is phi, and correspondingly this is how you can calculate the stream function value, which is x square minus y square minus y. Okay, so this is actually the stream function which many of you might have got here. Okay, so okay, minus of this minus, right? X minus of this minus gives you plus y square here. Sorry, plus y square here. Okay, because if you see minus y is here plus x square, and minus of minus gives you plus, so x square plus y square minus y. Correct. So this is the stream function value. Okay, so because this minus is also there, you have to multiply with this minus. So basically you will get the phi and psi functions directly like this if you use this little analysis. Okay, so this method is called Milne-Thomson method, which you use in complex numbers, where you replace x value with a z and y value with 0 actually here. Okay, and if you see, for example, okay, if you okay, so this is phi values and this is psi values. If this is in polar coordinates, for example, okay, if this function is in polar coordinates, then you replace this small r, because in this expressions obviously when you write in polar coordinates you will get r comma theta values, so you will replace r with z and theta with 0 in that polar coordinates. Okay, so once you replace small r with z and theta with 0, you will get the again the stream function and the velocity potential functions easily in polar coordinates. Okay, look, for example, I will give you one complicated function. You should tell me how it comes out. Okay, so let us suppose if I give you, for example, phi is this. If I ask you to calculate psi, okay, so phi is equal to ln, for example, okay, say ln root of x square plus y square. Okay, if I ask you to calculate psi value, psi is how much? If I ask you to calculate this function, for example, okay, so some ln root of x square plus y square, okay, I have asked you this and I am asking you plus psi, what is the value of psi basically. Now if you calculate dou phi by dou x, dou phi by dou y and integrating them again, it comes little complicated for you, correct? Because for this example you cannot calculate psi very easily like you have calculated in previous case if you know using partial differentiation, because these terms will give you some complex expressions actually. So but if you use this Milne-Thomson method to calculate, it is very easy. See, for example, f dash of z is equal to 1 by 2 root of x square plus y square into 2x. Okay, so this is the differentiation, which is u minus I times of v, which is dou phi by dou y, so 1 by 2 root of x square plus y square into 2y. So this is u, which is dou phi by dou x, and v, which is this value. Now if you apply Milne-Thomson method, so if you apply Milne-Thomson method, this y can be replaced with a 0, y can be replaced with a 0, so this y, this complete term is 0 now. So you have f dash of z is equal to 2 gets cancelled. If you replace x with z, this term is anyhow 0 because you have replaced y is actually 0 here. Then 1 by root of x square plus y square, z by root z. So if you see, z by square root of z square, which gives you 1 actually here. So f dash of z is actually 1 in this case. Clear? Yeah, you need not go to polar form basically. Okay, straight away you can write this. I think some error in differentiation, ln of something 1 by, okay, fine, yes, there is some error. Yes, we have taken square root of by forgetting log. Okay, so now if you differentiate correctly, 1 by root of x square plus y square into differentiation of square root of x square, 1 by 2 root of x square plus y square into differentiation of this with respect to x is 2x. Now it's fine. Okay, minus or plus, okay, minus I times of v. V is nothing but the partial differentiation of this with respect to y. So 1 by root of x square plus y square into derivative of root is 1 by 2 root of x square plus y square into 2y. So this is what you actually have, correct? Now it's fine. Okay, now it's fine. Okay, so basically log values are there. Now if you apply Milne-Thomson method, you should replace this x with z and y with 0. So if you replace y with 0 in these sums, you have these zeros here, so this imaginary part is completely 0. Now if you replace y is equal to 0 here, y is equal to 0, then 2 gets cancelled. You have 1 by root of z square, z into 1 by root of z square, z into z. Okay, so you can cancel z and z. So if you multiply dz on both sides and if you integrate, f of z is equal to, this is 1 by z, so log z. This is what you have for the complete complex potential function. So just now I have shown you the expression for ln z, how you will simplify that. So this ln z is nothing but ln root of x square plus y square plus I times of theta, which is tan inverse of y by x. That's it. Okay, so this is the stream function psi of x comma y. and this is the velocity potential function that I given you, phi of x comma y. So once you know this function, you can immediately get stream function very easily because of this simplification, putting y is equal to 0. And you know very clearly, if you calculate using dou phi by dou x partial integrations, answer is not this simple, you know this, correct? And this are actually simple profiles I am giving you, but let us suppose if they give you complicated profiles, sometimes you will see these expressions like phi of x comma y is equal to x square minus y square divided by root of x square plus y square. They'll give you these kind of expressions actually, okay? So when they give you these kind of expressions and if they ask you to calculate stream functions, it is very hectic job for you, okay? But if you understand carefully, this is again simple. If you directly calculate this, you will get z bar by magnitude of z, okay? Sorry, z square by magnitude of z actually here. This is the complex function. So if you this is the complex function, if you replace x with z, y by 0, all these things, you will get this result. So from this, if you simplify, you know, x square minus y square by root x square plus y square is the potential function, plus I times of 2xy by root of x square plus y square. This is the stream function, is what you will directly get if you simplify this result, okay? So that's how, if you know complex numbers, this velocity stream function game can be played very easily. Clear? Got it? Yes or no? And for a doublet, actually, if you see, when you place source and sink very close to each other, your complex potential function turns out to be m by pi times of z actually. Clear? So if these things are clear, we will go for the next question, okay? Okay, because generally you might not, you know, be very familiar with this complex numbers case, so that's why I'm just giving you some brief idea. But did you all understand how for this we have simply calculated this tan inverse of y by x? Yes or no? If you try to do in that way, u is equal to dou phi by dou x, v is equal to dou phi by dou y, then again equating and integrating partially, you know, you will end up with expressions like integral 1 by x square plus y square, all these terms, okay? So that need not be done in this case, okay? Understood? You see how simply 2-3 lines you found out what is stream function with simple calculations, okay? So that's why this is one very important technique for talking about complex potential functions, okay? I hope you are you know, listening to a few things for first time, okay? Okay, now let's go for the next question. So see, the potential function for a flow phi is given by 6x square minus y square meter square per second, where x and y are in meters. A streamline passes through the point a2 comma 3. The correct statements are, okay? So they are asking you for the correct statements. So first statement, phi is equal to 6 times of x square minus y square. 6 times of x square minus y square actually here. X square minus y square. By looking at this, can anyone tell me what is stream function? Just some random guess. You know, x square minus y square term comes if you square the z, correct? If you write only x plus iy whole square, then you will get x square minus y square. So by looking at this, can anyone just tell me what is the stream function value directly? Any technique? So please tell me what is the stream function value. Anyone can you know, just guess by looking at this function what is the stream function, because you see this is of the form 6 into z square, correct? Because x square minus y square term you will get only if you do x plus iy whole square, okay? So now can you please tell me what is stream function? When you square 6 times of 6 into z square, what could be the imaginary part? What could be the imaginary part? So please tell me what could be the imaginary part actually. Okay, no idea, fine. Okay, we'll take some time and we'll understand, okay? So see here, first let us calculate velocities. By default u is equal to f dash of z if you take, okay fine, let us calculate simply. Why to go for all these things? 12x and v is minus 12y, okay? So what is the point they have given you? U at the point, okay, u at the point, what is the point they have given you? 2 comma 3. So u at the point 2 comma 3 is equal to 12 times of 2, which is 24, okay? And here if you see v at the point 2 comma 3 is actually equal to minus 12 times of y, so minus 12 into y, which is 3, so minus 36. So if you do the square root of this, so magnitude of velocity at point a is equal to root of u square plus v square, which is 24 square plus 36 square. Let us take a calculator quickly, get calculator, okay? So 24 square plus 36 square, so this is the value. If you take a square root, 43.266 directly, 43.266 meters per second. So this is the velocity at point A directly. Yes, very good. It is 12xy, correct? Because if you see, phi is equal to f dash of z. If you calculate, f dash of z is equal to dou phi by dou x, 12x minus I times of v, which is minus 12y. Minus 12y. Okay. Now if you apply Milner-Thomson method, x is z, y is 0. So this term goes to 0 anyhow. So f dash of z is equal to 12 times of z. So if you integrate this, or by multiplying dz on both sides, this gives you f of z is equal to 6 times of z square. Okay. So 6 into what is z square? X plus iy whole square. If you simplify, you will get 6 times of x square minus y square plus I into 2xy. Okay. So the real part in this is 6 into x square minus y square, which is the stream function, plus I into 12 times of xy. This is the stream function. Okay. So this is the velocity potential function, which is already given here, which you can see, which is the stream functions. This is psi of x comma y. Okay. So this is how we can get the stream function. Okay. By looking at x square minus y square, generally if you know that this is z square gives you x square minus y square, you will immediately come to know the stream function value is 2xy into 6, which is 12xy directly. Okay. With this example, no partial differentiations and all these things again. Okay. So that's how we can directly get this relation. Now if you see the stream functions at any point, stream functions are given by f psi of x comma y is equal to constant. So this stream function is achieved by 12xy is equal to some constant. Now given this stream function is passing through the point 2 comma 3, then 2 comma 3 should satisfy this point. Okay. So this implies at 2 comma 3, what is the value of constant? 12xy, 12 into 2 into 3 is equal to c, which means c is equal to 2 3 are 6, 2 3 are 6, 6 12 are 72. So basically if you see, if you write the streamline equation, 12xy minus 72 is equal to 0. So if you cancel 112, we have xy minus 6 is equal to 0. It's a rectangular hyperbola basically. So this xy minus 6 is equal to 0 is the stream function value in this case. Okay. So add. Okay, so basically if you see this xy minus 6, xy is equal to 6 is the streamline passing through this point, and magnitude of velocity is 42 point something we got. So a comma d are the correct answers in this case, a comma d. Okay. So this stream functions can be easily calculated using this complex potential functions. Okay. That's it. Fine. Look, I have taken some small velocity profiles, but if you see, I explained you with one case that in this case, definitely, if you want to solve this, if you want to calculate this psi stream function using the normal technique, what you do by partial differentiations, then again integrating all this, you are not going to get this question in such a simple 2-3 lines, correct? So that's why this method is one of the very powerful methods for evaluating the stream functions especially. Okay. Clear? Okay. Now, shall we go for the next question? So shall we go for the next question? Is that clear to all of you? So please type in the chat box. Okay. Fine. Look, let us solve this question. The potential lines in case of a doublet are circles tangent to x-axis with center on y-axis, circles tangent to y-axis with center on x-axis, concentric circles with center on x-axis, concentric circles with center on y-axis. So let us see what is the correct answer in this case. Okay. So let us try to see what is the correct answer in this case. The potential lines, basically the equipotential lines they mean. Okay. So equipotential lines in case of a doublet. So what is a doublet basically? Let us try to understand here. Okay. So doublet, as I told you, doublet is basically source and sink of uniform strength, source and sink of equal strength, source and sink of equal strengths placed very closely, okay. So source, look, every combination of source and sink cannot form a doublet, okay, because source can be of some different strength, sink can be of some different strength, and let us suppose these two are far away, then it's not a doublet. Okay. So doublet is only in such situation where source and sink are placed very close to each other. Clear? Now if you see, so I told you what is the complex function for f of z if it's a source, m by 2 pi, if m is the strength, m by 2 pi ln z, for example. Okay. Ln z, like this, ln z. and f of z is equal to minus m by 2 pi times ln z. This is for sink, because this minus sign tells you the discharge actually flows into the things. Okay, so this is for sink and this is for source. Now you know doublet is nothing but superposition of these two elements, source and sink. Now if you want the complex potential function for this doublet, this implies f of z for doublet. If you talk about doublet, then you need to add these two things, correct? So if you add these two things, m by 2 pi sorry, this is m by 2 pi plus these two are not at same points, because obviously source and sink should be separated by some distance. So let us suppose if you have, for example, let us suppose like this is minus epsilon comma 0. For example, you have a source here, and let us suppose you have some sink here. Okay, so sink which is at the point epsilon comma 0. Epsilon is very small distance. Okay, they are placed very close to each other, for example. Okay, then in that case you see this value is nothing but ln z minus of minus epsilon, which is ln z plus epsilon for source, because I told you if this point is z naught, then you have to replace with complex number z naught. Okay, similarly here this point is actually z minus epsilon. Now if you simplify these two, if you add these two, you will have m by 2 pi times of ln z plus epsilon minus ln z minus epsilon. So log a minus log b can be written as ln epsilon minus e. Okay, so now you can write this basically. Now if you do certain mathematical simplifications here, means taking out z then cancelling out, and if you apply logarithm expansion, neglecting higher terms for Taylor series, if you do certain, there is certain mathematical analysis, and after that what you will get is basically you will get m by pi times of z actually. Okay, so this is what you actually get as the complex potential function for a doublet. Okay, whenever a source and sink are very much close to each other. I'm not doing that analysis as of now, because if you see, this is some mathematics that is involved here. You will take z common, then 1 plus epsilon by z divided by 1 minus epsilon by z. You will write this 1 minus epsilon by z as 1 minus epsilon by z whole power minus 1. Okay, once you write that, when you expand, you will neglect higher order terms. Then for the term which is remaining inside, you will apply logarithmic expansion, and again you will neglect higher order terms. This is some mathematical and Taylor series involvement that is there, but if you simplify, you will end up with such expression m by pi z. Okay, now let us see what they're asking you. This, if you see here, m by pi times of z. Now let us see what comes out actually. Okay, m by pi times of z, this is the function. So if you see, this has some equipotential part in it, and also plus some x comma y part in it. Okay, so you can understand very easily, but let me help you out with some small analysis. Okay, so if you see carefully here, let me convert to Cartesian now. Okay, because you already got the complex function, so let me convert to Cartesian. Can I write as z conjugate into mod z whole square here, because you see z into z conjugate actually gives you mod z, correct? So that's why if you see, if I multiply a mod z on top on the bottom, then I'll get z conjugate on the top multiplication divided by z into z conjugate. You see, z into z conjugate, if you see, x plus iy into x minus iy. So if you do the simplification, you will get x square plus y square, which is nothing but magnitude of this z whole square. In complex numbers, you might have seen this, correct? So can I replace this? If I have this function as m by pi z, then can I multiply a z conjugate on the top and bottom, and can I write m times of z conjugate by pi times of mod z conjugate? Yes or no? So please type in the chat box. Clear? Can I write this or not? So please type in the chat box. All of you, everyone should type in the chat box. Okay, now correct, I can write this. Okay, now if I can write this, yes, I can write this basically. So now if I can write this, now let us simplify m by pi, which is some constant. This m by pi is, let us take it some constant, because if source is defined and sink is defined, this m is some constant, pi is also constant. So c by mod z whole square, x square plus y square into z conjugate is nothing but x minus iy. So if you split this into real part and imaginary part, you have cx by x square plus y square minus or plus I into minus cy by x square plus y square. So if you see carefully here, this part is nothing but the equipotential part, means the potential function phi of x comma y, and this is nothing but the stream function, which is psi of x comma y. Now they are asking you, if you plot this for different values, What is the, so why subtraction of source and sink? Not subtraction, I have actually added them, but there is subtraction because of this minus sign. Okay, for sink you will have a minus sign because source, I mean in the case of sink, flow is actually towards in the negative direction of the radius. That's why we'll put a minus sign here for sink. Okay, actually I have added these two functions, but because of this minus sign it's appeared like a subtraction for you here. Okay, Abhimanyu? Okay, I hope it's understandable now. Clear? Now if you simplify this, you have this velocity potential function as cx by x square plus y square. Means basically if you know that this is of the form some constant divided by z directly, as I have given you for a doublet here in the beginning. If you observe, I have given you for a doublet, this is given by some constant divided by z. If you know this value that this complex function is of this form some constant by z, then directly as soon as you see this question, you will come to this part. Okay, then you will do a one line conversion. Basically the difference between these two is only single line. Okay, you have this one line. Now if you want to plot these things, let us see how we can write. If you want to plot the lines phi of x comma y is equal to some constant c1 say, then this gives you cx by x square plus y square is equal to some constant c1 for example. So you can write this as x square plus y square. If you multiply this here and if you divide this c1 here, c by c1 is some constant again, so minus k times of x is equal to 0. Okay, so this is the equation. So if you slightly adjust this equation, you can get x minus k by 2 whole square, because you are trying to convert this x square minus y k, x square minus kx into some quadratic term. So if you want x square minus kx term, you should write this. Okay, so plus y square, which is nothing but y minus 0 whole square. So what is the term you are getting excess here? K square by 4. Okay, so that k by 2 we'll write here. So can you tell me what does this equation represent? X minus k by 2 whole square plus y minus 0 whole square is equal to some constant by 2 whole square. So can you please tell me here what is this equation here? What is this equation? See, just 2-3 lines. This is just mathematical simplification I have done. Okay, so this is 2 lines. Look, if you know for a doublet, this is the velocity, this is the complex potential function which is c by z. Then just by one conversion you will get this phi values. So if you draw this different values for phi, then you will get this equation in 2-3 lines hardly. Okay, now this curves, they represent a circle because they are of the form x minus h whole square plus y minus k whole square is equal to some radius square. Okay, so now if you take a empty slide for example, let me explain you. Now see carefully here. If you try to plot this circle, tell me one thing. Now let us suppose if for example I take a point k comma 2, k by 2 here. Okay, so k by 2 comma 0, this is a point for the circle. Now let us suppose if I draw a circle with this center and radius also k by 2, then can I say that this circle actually touches this y axis? Can I say this? Yes or no? Because if you see, if this center is k by 2, then you got this radius is also k by 2, correct? Because if you see here, if center is k by 2, radius is also k by 2. If center value and radius is same, then can I say this circle actually touches the y axis actually, correct? Can I say this? Yes, y axis acts as tangent obviously, correct? So if you see for this circle, this line acts as a tangent here. Okay, let me erase this k by 2 comma 0 because just to make you understand I have written this. Similarly, let us suppose if I take some different values of k, for example k is equal to 2, if I take this point is 1 comma 0 and this is a unit circle. Now if I take k value as 4 for example, then I will get some different circle like this, center at 2 comma 0, but again this radius will be 2. Okay, so that's how, if you see, we will get one more circle like this basically here. Okay, fine, you will get circle like this. Did you all understand here what we are getting? Similarly, if you take k is equal to 8 for example, you will get different one more circle like this. So k is equal to 8. This is how you will get one more cycle. Clear? Similarly, if I take k as negative values, for example, okay, then if I take k as negative values, the center gets shifted to the this side. Okay, so the center gets shifted to the other side basically here. So you will get a cycle like this. Similarly, you will get one more cycle like this, and so on. It goes on actually here. Okay, so that's why if you see the equipotential lines, we have made some equipotential lines, correct? So this is basically for some value of phi. phi is equal to some constant 1. This is for some different value of phi, C2. This is for some different value of phi. Similarly, this is for some other value. This is for some other value. So basically in this case, if you see the equipotential lines, the lines with constant values of phi, means basically the curves, these circles are such that the centers are on x-axis and actually the y-axis act as tangent to all these circles. Clear? So that's how we can say for this configuration, the potential lines in case of a doublet, means basically if you have a source and sink at very close to each other, you will get circles tangent to the y-axis with centers on x-axis. So B is the correct answer in this case. Okay, you can clearly see these are not tangent to x-axis, and first of all these circles are not concentric circles. Okay, they don't have the same center, but of course their centers on x-axis. That's it. Okay, so with this understanding, simply look hardly 3-4 lines you have done. If you know this function directly, then you know this, then just converting into circle. Okay, then if you see this circles is basically how we actually get this. Clear? So please type in the chat box, is this clear to all of you? Did you all understand how we have converted this into from this complex numbers into Cartesian x plus iy coordinates? Okay, clear? Now let's go for the next question. Okay, I hope it's fine. So next question, let us see this question. A two-dimensional source of strength 1.8 meters square per second has been placed at the origin in the stream of inviscid and incompressible fluid moving with a uniform velocity of 0.6. The resultant velocity of fluid in mm per second at small r is equal to 0.75 and theta is equal to 120 degrees is dash. So this is what they're asking you. Okay, so basically there is a source which is placed at one point, and also there is also one uniform flow passing in that flow field. Okay, so what could be the net flow? There exists definitely some net flow, and for that net flow that existed at this radius of 0.75 and at this value of theta is equal to 120 degrees, what is the velocity actually? Okay, so let us calculate this. So basically if you see, this is a superposition of a source and a uniform stream, basically uniform velocity stream at 0.6 meters per second, moving with a uniform velocity 0.6 meters per second. So if you do the velocity potential function f of z, if you write this f of z, let us see what comes out. F of z is basically equal to the complex potential function for the source plus the complex potential function for the uniform flow. Okay, now if you see them, f of z for source function has m by 2 pi times of log z, because it's given the source is placed at origin, so z naught value is 0. So if you see, we have m by 2 pi ln z is what you have, plus uniform flow. I told you for uniform flow this is u times of z, so 0.6 times, which is u times of z. Let us suppose if you write this u times of z. So if you slightly simplify this, m by 2 pi times of uz, this is the complex potential function for the net flow, because for uniform flow this is uz, for source this is m by 2 pi ln z. Okay, now if you want velocities, for example, f dash of z is equal to u minus iy, u minus iv. So if you calculate the magnitude of this complex number, that's it, you will get square root of u square plus v square, because if this is some complex number, then the magnitude of this can be calculated with square root of u square into v square actually here. Okay, so particular of this potential, I didn't get you. So particular of this topic, okay, in this particular topic, potential flow, which book we have to refer? Honestly speaking, frankly I'm telling you, some basic idea in terms of complex numbers is present in 1 or 2 books, but normally this you might have seen in many textbooks, this potential flow is explained you with the help of this x and y equations. Basically instead of using complex numbers, they have just used some xy equations, like basically the classical methods what we talk about in kinematics and all. But there is one book which can give you some basic introduction, Kundu and Cohen. Okay, there is one very good book, Kundu and Cohen, that's one good book. But whatever I am teaching you majority is from the professor who taught me fluid mechanics at IIT Madras. Okay, so from there I am teaching you this. Okay, in books you don't find this in this much detail, honestly speaking, because I have searched books. In Frank and White you have some little idea, and in Kundu and Cohen also you have some basic idea about this. Okay, but this is the simplest method that I've learned for fluid mechanics from a professor at IITM. Okay, so that's what I'm teaching you. Clear? Okay, fine. Okay, so look here, Kundu and Cohen is one book you can go through if time permits for you. Okay, fine. So let us see this. So if you want to calculate f dash of z, so f dash of z is equal to m by 2 pi. Differentiation of log z is 1 by z, so which is this, plus differentiation of uz is nothing but u. So this is the complex potential function for f dash of z. Okay, so this is for the f dash of z. Now if you slightly convert this, what they're asking you, the velocity at r is equal to 0.75 and theta is equal to 120. So let us do one thing, let us convert this into polar coordinates because they have given you in terms of r and theta. Okay, so m by 2 pi times r into e power I theta is what you can write plus u. So this can be written as u plus m by 2 pi r times of e power minus I theta is what you have actually here. Okay, now if you calculate carefully here, you know this, if I write this as, you know, this is what you have. So you are, for example, you are, simply you can convert this to xy coordinates, for example. Okay, so fine, you can do anything, you can do polar coordinates or you can do Cartesian coordinates. Let us convert this to polar coordinates, for example. Okay, so u plus, if you want to take u power if you want to take e power minus I theta common, you can write u, capital U, into e power I theta plus m by 2 pi r times of e power minus I theta. So you can take this common. Now if you make a minus sign adjustment here, minus and minus, okay, or okay, if you want to make this minus sign adjustment, initially you have plus here. So if you have plus here, you can write that plus as minus and minus I basically. So this minus of minus I gives you plus 1 again. So this is of the form u r, this is of the form small u r, and this is of the form u theta. Okay, because I told you this f dash of z in polar coordinates can be converted to u r minus I times of u theta. Okay, this I let us write outside. So minus I let us write outside because initially I told you this minus I is outside. So minus I times of minus m you can write. Okay, so minus of minus, there is one more I na actually. Just a minute, please adjust this minus sign carefully. If you want to take e power minus I theta common, you have e power I theta plus m by 2 pi r. So this plus m by 2 pi r can be written as minus I times of minus, because minus into minus is okay, we need to have one more I. Okay, so plus, you need to convert this into minus signs. So we can write I times here, instead of m you can write I. Okay, so instead of m you can write I actually here. Okay, so I times of m. Okay, now this is fine. Minus e power u into e power I theta minus I times of this im by 2 pi r. Okay, so this is how you can actually write here. Okay, now if you see, this is u r is obtained by this expression u into e power I theta, and u theta is actually obtained by this expression I times of m by 2 pi r. Okay, so these are the two expressions that you have. Now if you want to calculate this magnitude of this velocity, you know, this can be written as a root of u r square plus u theta square also, because if you see in this initially splitting, I have told you, in this case if you see, this is also a rectangle because radius and theta is a rectangle, this is also a rectangle. So if you see, for this velocity vector, this means if you apply Pythagoras theorem by this yellow triangle or by this green triangle, both give you the same hypotenuse value. Okay, so once you have this u r and u theta values, so see here u r and u theta. So let us calculate this magnitude of u r. Magnitude of u r is nothing but magnitude of u into e power I theta. So magnitude of u into magnitude of e power I theta, and you know, magnitude of e power I theta, this complex number magnitude is 1 because e power I theta is cos theta plus I sin theta. So if you calculate the magnitude of that complex number, square root of cos square theta plus sin square theta is what you'll get. So that is 1. So this is nothing but u. So what is u? u r is nothing but, okay, they have given you some value now, u r, this is moving at 0.6 meters per second. So this is 0.6 meters per second. Now coming to u theta, magnitude of this u theta, magnitude of I is 1, m, so what is the strength that's given of the vertex, this source, 1.8. okay, so 1.8 divided by 2 pi into radius value. So what is the radius they have given you? 0.75. okay, so if you keep 0.75 here, Then let us see what is this value. This is 0.6. So 0.6 by pi times of 0.75. Okay, so let us calculate this value. What is this value? 0.6 divided by 0.6 divided by pi into 0.75. Pi into 0.75. Okay, so this is what you get, 0.2546. 0.2546 meters per second. So now if you want the velocity vector at that velocity value at that point, then you can calculate root of ur square plus u theta square. Okay, सर आर स्क्वायर में कब सॉल्व कब करवाएंगे विथ कॉन्सेप्ट? अच्छा, you want me to solve some questions of this R square me? Okay, we'll see if there is some time before get examination. We'll try to put this. Okay, so now if you calculate these values, 0.6 square of this plus 0.6 square, 0.6 square. Okay, so if you simplify, this is the value. So 2.612 is the velocity here. Okay, so 2.6. Okay, I think we missed something. Just a minute, we missed some value here. So I is actually there. So basically in this function, let us see carefully. So ur value is given by this function u into e power I theta. So this is fine. So coming to this value, we have this another pair. Okay, so let us do one thing. Instead of this separation, because we have some ambiguity with this I, we'll do one thing. Okay, instead of doing this thing, because if you have some doubt with this plus or minus I signs, let us do one thing. Let us try to split this uniformly here. So u plus m by 2 pi r times cos theta minus I sin theta. So if you split this perfectly, then you'll get this expression f dash of z is equal to u. Look, in this complex number, u plus m by 2 pi r cos theta is the real part. U plus m by 2 pi r cos theta, this is the real part, correct? Minus I times of m by 2 pi r sin theta, this is what you actually have, correct? Because if you write e power minus I theta as cos theta minus I sin theta, you directly get this. Okay, so now this is anyhow a real term. So m by 2 pi r into cos theta, this comes for the total support of this real term minus this complete term minus m by 2 pi r times of sin theta. So this is of the form u minus iv. So if you want to calculate the magnitude of this velocity vector, you can calculate magnitude of this velocity vector is equal to, this is u and this is v. So u minus iv form. So magnitude of root of u square plus v square. So let us calculate what is this u and v values. U is equal to capital U, which is 0.6 plus source strength is 1.2 by 2 pi smaller is 0.75 into cos theta. Theta is 120, so cos 120 is nothing but minus cos 60, so minus 1 by 2. This you have to simplify for u in meters per second. Similarly for v, you have m by 2 pi r into sin 120. Sin 120 is root 3 by 2. So let us, because rather than adjusting the minus I and all, let us go for this straight away. Okay, the expressions are very clear in this case, because if you just simplify, we'll get this answer. Okay, now let us simplify this. If you simplify this, 4 cancels this 0.3 times, 2 cancels this, and again 4 cancels this 0.3 times. Okay, let us do the simplification. First, this value minus 0.3 by pi into 0.75. Okay, so minus 0.3 divided by pi into 0.75. Minus 0.3 divided by pi into 0.75. So if you do this calculation, we got minus 0.127. So minus 0.127 plus 0.6 plus 0.6, 0.47267, 0.47267 meters per second. Similarly here, if you calculate 0.3 into square root of 3, 0.3 into square root of 3 divided by pi into 0.75 divided by pi into 0.75. So if you simplify this result, 0.2205, 0.2205. So these are the u and v component velocities. So 1.8, not 1.2. Acha, strength is given 1.8. Oh, sorry. Yes, this is 1.8. Okay, so we'll do this calculation once again. If you put 1.8 here, then definitely this 2 can cancel this 0.9 times. This 2 will be remaining as it is here. So plus 2 into pi. This is 2 pi. Okay, so yes, I think this is what we can do. Similarly here also, this is 1.8 and then this 2 lies as it is. So if it is 1.8, then 2 cancels this 0.9 times. So let us see. 2 into 0.75 is 1.5. Okay, so let us see these calculations. So definitely these values will be changing because we have substituted some incorrect value for strength. So let us suppose if you do this calculation, minus 0.9 divided by minus 0.9. So this value divided by minus 0.9 divided by 2 into 0.75 gives you 1.5. Okay, so 1.5 into pi, 1.5 into pi. Okay, so 1.5 into pi minus 0.1909 minus 0.1909 plus you have 0.6. Okay, so plus 0.6, so 0.4090 meters per second. Okay, next coming to this guy, 0.9 into square root of 3, 0.9 into square root of 3 divided by 0.9 into square root of 3 divided by pi into 1.5 divided by 1.5 into pi. Okay, so this is the value 0.33709, 0.33709. so is this values correct now? So please confirm. Okay, so these are the values 0.4090 and 0.33709. so if you calculate the magnitude of this velocity vector, so magnitude of this velocity vector is equal to squares of these two quantities and taken a root. So square of this guy plus 0.4090 square, 4090 square. Okay, so you have taken this value. So if you take a square root of this, we got 0.52603, 0.52603 meters per second. Okay, this is in meters per second. So let us check what is the answer. B. Okay, 526. Did they ask in mm per second? Okay, they are asking you in mm per second. We got in meters per second. You can just convert it. So if you get it in meters per second, this is nothing but 526.03 mm per second. That's it. Mm per second. Okay, so this is how we got the correct answer, 526.03 mm per second. You see, it's very simple. Once you know this potential function and this potential function, you have got this expression for f dash of z, then you have converted this to u minus iv form. You have calculated the magnitudes. That's it, finished. Okay, clear? Did you all understand how this is done? Very simply. Look, this part is very simple. Only 1 minute it takes hardly. If you know these two functions, then differentiation of this m by 2 pi, derivative of log z is 1 by z plus u into derivative of z is 1. That's it. Okay. So this z, since it's given in r and theta form, you write r into e power I theta plus u. This can be written as u plus m by 2 pi r into e to the power minus I theta. So if you calculate this, this is the value. Okay. So once you identify this u and v, just substitute the point, calculate u value and v value, then calculate the magnitude of this. Okay, simple. Normally, you know, you might have seen in case of flows, let us suppose if you do in directly as per the methods that is available, then first of all, you know, it's very big. You need to remember a few points. You need to write some functions in complicated forms of x comma y. That there happens a lot of things actually. Okay, so without all that, you have directly calculated. Okay, liking this method of partial, I mean this complex numbers? Clear? We need not write big expressions actually, because since log is involved, normally you are expected to write log root of x square plus y square plus I times of tan inverse y by x, all these things, but you know, not needed right now. Okay, you see, very simple. Just differentiation, split it into u and v form, get the component values. That's it. Okay, now let us go for the next question. Let us see the stream function psi for a uniform flow past a circular cylinder of radius a in polar coordinates is given by psi is equal to some function they have given. The resultant velocity on the cylinder at theta is equal to 90 degrees is dash units. Okay, they are asking you what is basically the velocity value. Okay, so directly stream function is given. If you want, you can directly calculate using this partial differentiations. Okay, you know, let us go with partial differentiations only simply. Okay, let us see, some velocity profile is given, flow past a circular cylinder in this case. So basically it's like a combination of doublet and a vortex flow. Okay, doublet and a doublet uniform flow, and basically some doublet and you know, this is flow past a circular cylinder, correct? So doublet plus uniform flow. Okay, so if you do this, let us see. Okay, so let us see basically here, f of z is equal to phi plus I psi. F of z is equal to phi plus I psi. You have this. So what is f dash of z? I given you u r minus I times of u theta into e power minus I theta. Okay, so this is the case. So here if you see, this is the complete function, means u r into e power minus I theta minus I times of u theta into e power minus I theta. You can calculate the magnitudes once you calculate these complex numbers. Okay, but how you calculate these complex numbers, u r and u theta, how you can calculate them? Just by this stream function. Okay, so you know u r is equal to, normally in case of, okay, let me take the next slide. So if you see, if velocity potential is given, then how you calculate u r? U r is equal to dou phi by dou r. U theta is equal to 1 by r times of dou phi by dou theta. Okay. Now, if you see, this phi and psi satisfy the Cauchy-Riemann equations. Phi comma psi satisfy Cauchy-Riemann equations. So these functions, since they satisfy Cauchy-Riemann equations, Cauchy-Riemann equations. So in this case, if they satisfy the Cauchy-Riemann equations, then you know dou phi by dou r is equal to 1 by r times of dou psi by dou theta, and dou phi by dou theta is equal to minus r times of dou psi by dou small r. Okay, so this is what you actually know. Now if you see, this u r is nothing but dou phi by dou r, which means u r can be calculated using 1 by small r times dou psi by dou theta directly. So this is how you actually calculate radial velocity in the flow. Similarly here, dou phi by dou theta, dou phi by dou theta is nothing but small r times of u theta. So small r times of u theta is equal to minus r times of dou phi by dou r. This is what you have. So small r and small r, if you cancel, you have u theta is equal to minus 1 times of minus dou psi by dou r. So this is how, if a stream function is given to you, how you calculate radial and theta velocities basically. Okay, so this is how basically you calculate. Okay, 16 is the answer. I don't know, let us check. Okay, so now if you see, what is the stream function that is given to you? Stream function they have given you is 8 times of 1 minus a square by r square, r square by a square, na? Okay, a square by r square into r sin theta into r sin theta. Okay, now if you see, let us calculate your radial velocity is equal to 1 by small r times of dou psi by dou theta. Dou psi by dou theta is how much? 8 1 minus a square by r square into smaller into differentiation of sin theta is cos theta. That's it. U theta is how much? Minus dou psi by dou r. Dou psi by dou r, how you will do this? 8 times of sin theta is constant in that case. So first function into derivative of second function, small r, is 1, plus second function into derivative of the first function, 0 minus 2a square by r cube. Okay, so this is what you actually have here. Okay, so r into differentiation of this is minus a square is constant, differentiation of r power minus 2 is nothing but minus 2 divided by r cube. Okay, so now if you simplify this result slightly, this r remains as r square here. So 1 minus 3 r square, correct? So you have 1 minus 3 a square by r square actually. First function into derivative for second function plus second function into derivative of the first function. So derivative of 1 is 0 minus a square is constant. So derivative of r power minus 2 is, I think there comes a plus sign here, no? Yes or no? There comes a plus sign here, correct? So there comes a plus sign because 1 minus has to be multiplied. So 0 minus a square by r square into minus 2 by r cube. So there comes a plus sign here. Okay, so if it comes a plus sign, then 1 minus a square by r square plus 2 times of a square by r square. This gives you minus of 8 sin theta times of 1 plus a square by small r square. So this is the expression for u theta. Okay, so this is the expression for u theta. So this is for u theta and this is for u small r. Now what are the points where they want these values? Okay, so they want these values at the location. Yes, positive sign comes out, correct? So you want these values at, they have asked, on the surface of the cylinder at r is equal to a and theta is equal to how much? On the resultant velocity on the cylinder. So if it is on the cylinder, then if the cylinder is of radius r is equal to a, then the point comes out at a radial location of small a, okay, and at theta is equal to 90 is dash units. Let us calculate this. So if you see at r is equal to a, theta is equal to pi by 2. What is ur value? Small ur, because if you see small ur is equal to how much? If you put theta is equal to 90, then definitely this cos 90 is 0. So if this term is 0, the complete term is 0. It is 0 actually here, okay. And u theta is also equal to, if you put theta is equal to 90, then this value is 1, and if you put a is equal to smaller, or smaller is equal to a, then this term gets cancelled. So 2 times of 8 minus 16. So this is minus 16 units. Minus 16 units, which means in this flow, means basically in this velocity profile, if you see in this velocity profile, you have, if you want to calculate the magnitude of f dash of z, you know, this is nothing but magnitude of this complex number u r into e power minus I theta. And basically if you see, if you see basically here minus I times of u theta, okay. So this is what you have, e power minus I theta, this multiplication of two complex numbers. Then in that case we have this value is 1, as I told you. So magnitude of ur minus u theta, this gives you square root of u r square plus u theta square is nothing but the magnitude of the velocity actually, okay, in this case. So this gives you the magnitude of velocity. So anyhow, if you see u r is equal to 0 and u theta is equal to minus 16 units, okay. So if you want to calculate magnitude of the resultant velocity, root of u square plus v square, which gives you 16 units in this case, okay. So which gives you 16 units in this case. Also, if you slightly think, even before doing this analysis, you will come to know that radial velocity is 0, okay. How? Look, I will tell you. Without performing this analysis, if you try to understand this situation, let us suppose there is a cylinder like this, and it is flow past a cylinder, means there is some flow which is coming like this and leaving, okay. For example, there is some flow which is coming like this and leaving like this. Now tell me exactly, if you take a point here somewhere, for example theta is equal to 90, let us say at this point, for example at this point theta is equal to 90, let us say, if you measure in the direction of the flow, this is flow angle 0, so 90, let us suppose. At this location, will there be any flow which tries to enter in the radial direction? Means if you see this is a cylinder like this, so at this location, if you see carefully, will there be any flow which tries to enter in the radial direction here? Please tell me, please type in the chat box, at this location, will you have any flow which tries to enter in the radial direction here? Everyone should type in the chat box, come on, you can just answer this. At this point, you cannot have any flow which can penetrate into the cylinder, so obviously the radial component of the flow is actually 0. You only have the tangential component, because exactly at this location, at this top location, the fluid will try to have a tangential velocity like this, okay. So you have the value of u theta, but you don't have the value of u smaller actually here. Clear? Okay, fine. Okay, I hope it's clear to you. So basically if you check, we get the answer to be 16 units, okay, which is given here 15.5 to 16.5. But because of this particular velocity profile and these equations, look, these equations are very, very important, because if you miss one minus sign or if you miss one smaller, that's it, your story is finished, okay. So you should be a little careful when applying these equations, especially in this polar coordinates. Clear? Since I have written this many times, you know, it's very handy for me, but if you are facing any difficulty, please practice these equations sometimes, okay. And it's very simple, they basically come from the Cauchy-Riemann equations, and normally when I'm taking any maths course for you, I'll definitely show you how these equations comes out in mathematics, okay. Here in this fluid mechanics, we are just using the results, so we are not talking about anything, okay. Clear? Punab, Pritam, Abhimanyu, Nikhil, okay, fine, Vishal. So let's get to the next question. A source at the origin and a uniform flow at 5 meters per second are superimposed. The half body which is formed has a maximum width of 2 meters. The width of the body at the origin is dash in meters. So as I told you, this uniform flow plus, you know, superpositions. I have told you some superpositions. So this uniform flow plus source, they give you something called Rankine half body, okay. And I told you this is the case. So, and here if you see, this is the maximum width, this is the maximum width actually here. Okay, so let us try to understand this situation. I'll take some time, I'll spend some time, and let me explain you how this rank and half body can be analyzed. Okay, so yes, see here. Okay, there is some time, we will talk about it. So see here, let me take a new slide first. Okay, now let us see, you have some two-dimensional flow. Okay, so you have certain flow like this. This is x-axis minus x, y minus y. Now this is a two-dimensional situation where there is some flow. Now tell me, what do I superimposed? A source at the origin and a uniform flow. So basically at this point there is a source and also there is some uniform flow along this. Okay, now if you talk about the complex potential function f of z, this is f of z of uniform flow plus the complex potential of source, because these two are superimposed. Okay, so let us see what we have. So if you simplify this, for example, let us see what comes out. This is uz plus, let us suppose if the strength of the source is m by 2 pi ln z, because this is placed at the origin. Okay, m by 2 pi ln z. Now if you see this complex potential function, if you try to analyze certain things, then let us see what comes out. This f of z is equal to, if you write in terms of polar coordinates, you have u into r e power I theta plus m by 2 pi times ln r plus I times of theta, and this is what you have. Similarly, if you see this r into e power I theta term, okay, so if you expand slightly, u r times of cos theta minus I sin theta, then this term comes out like u r cos theta plus m by 2 pi times ln r plus I, if you take common, you have u r sin theta plus m theta by 2 pi. So this is how you will get the potential function and also the stream function in terms of small r comma theta. Okay, so this is phi of r comma theta, basically in polar coordinates. Similarly here, if you see, this is stream functions in case of r comma theta. Now tell me one thing, if I ask you this, so stream functions are given by this function in case of this superposition flows. Means if you don't want to draw some streamlines, you need to take different values of theta and different values of r, and you can form this. Okay, now tell me one thing, so stream function is given like this. So stream curves are given by u r into sin theta plus m by 2 pi is equal to constant, basically. Okay, so stream curves are given by this equation. So if you make this stream function is equal to some constant, then for different values of constants you will get different functions. Now there is one particular value of this c which is some important in understanding this. Okay, if this stream constant is equal to m by 2, which is, means let us suppose if this value of c can be arbitrary, you can take any value, but this c is equal to m by 2 has some special appearance here. Okay, look what it is. If you try to take c is equal to m by 2 and if you try to plot the curve, your curve looks something like this. It increases to some length and then after it gets flatter. Then after it gets flatter like this. Okay, so it gets flatter. Similarly here, if you draw this curve, it increases and at one particular point this becomes saturated like this. This is how we have, and of course this is how we actually say this case as the Rankine half body case, because this is looking like a half body, because this is equation of a streamline actually. So this is equation of a streamline where psi is equal to m by 2. Okay, psi is equal to m by 2. So if this is a streamline, then flow cannot enter this, means practically there can be some flow, this uniform flow is there, this source is there, but practically speaking this no flow from outside can enter this, at the same time no flow can cross this, because there cannot be flow across the streamlines. Okay, now if you understand this, here I am interested to know about few quantities. This is symmetric, of course. Okay, this is symmetric. So if this is symmetric, let me ask you one thing. Let us suppose if I take a point here, for example, which is at very large radius. Okay, so if I take some point here at very large radius, if I try to draw a line like this, can you tell me at some large radius this value theta, if I call this value theta, as r tends to infinity, means let us suppose if r is tending to infinity for a large length, can you tell me what this angle theta tends to? Try to understand something here. Okay, so I'm talking about the Rankine half body, so please tell me if this point is going very far, means you know after a certain point what happens, this is a constant width. So if I want to connect this horizon with some point on the streamline, then can you tell me as r value increases, means for very large value of r, this theta, what does this theta value tend to? All of you should type in the chat box. Yes, very good, it is 0. Okay, so theta tends to 0. Theta tends to 0 here. Okay, so theta tends to 0. Now let us try to understand one thing here. So this value means at this location, so at this location, okay, so at this location, this is x. So now if you see at one particular point, if you talk about this width, half width for example, okay, so this is symmetric anyhow. So if you talk about this width, which is half width, okay, so this half width value is nothing but, if this is smaller, then this half width is nothing but r times of sine theta. So the total width of the Rankine body is nothing but w. If I call this, w is equal to 2r times of sine theta. Okay, now let us see what is this value. Let us see what is this value. The equation is given by this curve. So if you take, because I just don't want to mug up the things, I want you to know. Okay, so see here, if you take this equation at value of m by 2, which is this curve basically here, so let us substitute u times of r into sine theta plus m by 2 pi times theta. So this value is equal to, there is one theta, no, this theta should be there, sorry, this theta also should be there, no? So m theta by 2 pi is equal to m by 2 for this constant value. Now if you want to calculate this smaller value, let us see what comes out. U into small r into sine theta is equal to, if you simplify this, m by 2 minus m theta by 2 pi, correct? So if you take m by 2 outside, we have pi minus 1 minus theta by pi. So pi minus theta divided by pi is what you actually have here, 1 minus theta divided by pi. So this implies u times of r into sine theta. So this implies radius at that location, r is equal to, means at some very large length, r is equal to m by 2u sine theta into pi minus theta divided by pi is what you have, correct? So this implies small r is equal to m by 2 pi u. If you take this guys out, you have pi minus theta divided by sine theta. Okay, so this is what you actually have. Okay, now if you see carefully here, if you apply this limit theta tends to 0, because you know the theta is not exactly 0, but it's going to be very small, then if you put theta is equal to 0, this expression turns out to be, if you put theta equal to 0, this is pi divided by sine 0, this is also 0, sorry, theta tends to pi. Let us suppose if you put theta tends to pi, limit theta tends to pi here, because, just a minute, let me write elaboratively. So you get pi minus theta divided by sine theta. Okay, you have this expression. So limit theta tends to pi is what you have, for example. Okay, so this is the line corresponding to theta is equal to 0, let us say. So theta is equal to 0. So let us suppose you are talking about this point. So let us suppose, and for example at this point also, in this direction, at this point. Now if you apply this limit theta tends to pi, now if you put theta equal to pi, this total limit gives you a 0 by 0 form actually. Okay, so this total limit gives you a 0 by 0 form, of course. So if you apply 0 by 0 form, if you apply L'Hospital rule, you will get this R value is equal to m by 2 pi u times of this turns out to be minus 1 actually here. Okay, so this turns out to be minus 1. So this is nothing but when theta tends to pi, this is the radius here at this value. Similarly, when you put theta is equal to 0, when you put theta is equal to 0 here, this value turns out to be pi by 0, which is infinity. R value tends to very much infinity. But let us suppose if theta tends to 0 is what if you substitute, this small r value is giving you minus m by 2 pi u is what you are getting. Okay, means basically this radius is minus m by 2 pi u. Similarly, if you put theta is equal to pi by 2, for example, in this case, then what you will get, I'm trying to tell you about lengths at different locations. So at theta is equal, at theta tends to pi, we have r divided by 2 pi mu. At theta tends to pi, we have r tends to minus r value is equal to, how much is this? R value is equal to minus m by 2 pi u is what you have. So this distance which is here, this distance is nothing but m by 2 pi u. Okay, so m by 2 pi u is this distance. This distance is m by 2 pi u. M by 2 pi u. Similarly, if you take theta is equal to pi by 2, so 1 will come. So 1 not minus 1. Okay, where it is you're talking? Where? Minus 1? M by 2 times of pi minus theta by pi, correct? U r sin theta is equal to m by 2 minus m theta by 2 pi. So m by 2 if you take out 1 minus theta by pi, so pi minus theta by pi is what you have. So small r is equal to m into pi minus theta by 2 u times sin theta pi, correct? So theta tends to pi. Okay, this comes out to be plus 1, correct? So yes, this is plus 1. Limit value is plus 1, correct? Because cos pi is minus 1, so this is limit. Okay, so this point at theta is equal to pi is at a radius of, if theta is equal to pi, then this comes out to be something like this. If theta is equal to pi here, then if theta is equal to pi, then this length is m by 2 pi u is what you get here. Okay, so theta r is equal to m by 2 pi u, m by 2 pi u. Similarly, at theta tends to pi by 2, at theta tends to pi by 2 means if you want to calculate this dimension means again same, of course I didn't draw the curve symmetrically, but you know this graph is completely symmetric. So let us suppose if this distance is a, for example, if you want to know this distance, okay, means at this location if I name two coordinates a 0 comma a and 0 comma minus a, then you know this length is 2a. If I want to calculate what is this height a at this point, you know this is theta tends to pi by 2. So when theta tends to pi by 2, this limit, because this expression is same for any value of r, this is what we have identified. Okay, so this is what we have identified here. So at theta tends to pi, we have observed this is the radius. So at theta tends to pi by 2, if you see r value is equal to limit, okay, first of all let's pull out the constants. M by 2 pi u is constant, m by 2 pi u is constant. Limit theta tends to pi by 2, limit theta tends to pi by 2, pi minus theta divided by this sin theta. Okay, so if you see this value gives you a pi by 2 again. Okay, so this value is equal to r is equal to m by 2 pi u times, when you put theta is equal to pi by 2, it's simple, pi by 2 divided by 1, so you have a pi by 2 totally. Okay, so this pi and pi gets cancelled, so this is m by 4 times of u actually here. Okay, so if this is m by 4 u, then this total distance is m by 2 u, means you can understand one thing, pi by 2, correct? Yes, this limit is pi by 2. So if you simplify this, you know this length is such that this length is actually total length. That's how, if you see, it's like a very small some curve that's such that this length will be equal to this total length. Okay, so m by 4, pi is also there, na? Pi got cancelled, right? So m by 4u is what you actually have. Okay, so there is a pi difference, so this smaller at this location is m by 4u is what you have, means this distance, what can you write? This distance a is nothing but m by 4u. So if you want the total distance, this is m by 2u. Okay, pi won't be there in that case, m by 2u. Now if you want to calculate this distance at theta tends to pi, let us see what we will calculate. sorry, at theta tends to 0. If you put theta tends to 0, you will get pi by 0, which gives you a infinity actually. Okay, infinity value is what you will get. But and obviously we know at theta tends to 0, this r value tends to infinity, very large value. But of course, to avoid the infinity, we'll use something at theta tends to 0. At theta tends to 0, this smaller value is actually equal to m times of pi minus theta divided by, we have 2 pi mu 2 pi u into sine theta is there. This sine theta, can I write sine pi minus theta here? Can I write sine pi minus theta? So please type in the chat box. Can I write sine theta value as sine pi minus theta here? If I write sine pi minus theta, and let us suppose if I put theta tends to 0, limit theta tends to 0, because sine theta is same as sine pi minus theta. So if I substitute this, then if I apply the limit theta tends to 0 actually here, this value gives you smaller is equal to this m by 2 pi u can be taken out. M by 2 pi u can be taken out here, and if you take m by 2 pi out, then theta tends to 0 gives you basically theta tends to 0. Okay, so theta tends to 0 gives you pi divided by sine pi is what you are getting, right? Just a minute, you have pi minus theta on the top and sine pi minus theta on the bottom also. So we'll put limit theta tends to pi here. Okay, sorry, we'll put limit theta tends to pi. Okay, so limit theta tends to pi actually here. If you replace here, theta tends to pi, because in order to make this 0 by 0 form for some finite conditions, let us suppose if theta tends to pi here, in that case, then in that case, if you see m by 2 pi u times of the differentiation of this is minus 1 divided by cos pi minus theta. So this gives you a quantity which is 1 actually here, correct? So m by 2 pi mu into 1, correct? There will be 1 pi also here. Just a minute, we need to calculate this. Theta tends to 0. At this theta tends to 0 here, sorry, theta is tending to 0 as it is. So if theta is tending to 0, we have pi by sine pi minus 0. So pi by just a minute, I think we have messed up some value here. This is the function. So this function, if you want to calculate at theta tends to 0 and r tends to infinity, correct? So this value we need to calculate. So if you calculate this value, this is m by 2 pi u into m by 2 pi u into, let us see, if you take m by 2 pi u, we have this expression sine pi minus theta is there. So sine theta can be written as sine pi minus theta, and also this pi minus theta in that case. Okay, so if you put theta is equal to pi, then you are going to get 0 by 0 form, correct? So then you are going to get 0 by 0 form if theta is equal to pi. Yes, because if you put theta is equal to pi, you will get 0 by 0 form. Yes, we'll do one thing. We'll substitute theta is equal to pi here. Theta is equal to pi, we are substituting. So theta tends to pi. So if you write theta tends to pi, then in that case, you are going to get 0 by 0 form. So if you apply L'Hospital rule here, we'll get differentiation. Pi, differentiation is minus 1. Differentiation is minus 1 actually here, because this is pi. So if you apply theta tends to pi, and if you do the differentiation, we'll get pi divided by, correct? So just do this calculation carefully once. Yes, we have already calculated, but just what I'm trying to do is, let us suppose if you flip this, means basically if you take this Rankine body, in this case theta tends to 0, if you substitute, let us see what comes out here. So when theta tends to 0, let us do one thing. We have calculated that theta is equal to pi, right? So at this step, we need to do some analysis here. So at theta is equal to pi, or at theta is equal to, we'll do one thing. Okay, you want this height. So if this is r sine theta, so let us calculate this value of r times of sine theta. Okay, so we need this sine theta expression. So let us calculate r into sine theta expression, for example. Okay, so if you calculate this r into sine theta expression, just a minute, let us see, r into sine theta expression. Okay, fine. Okay, so let us get the width directly. Instead of calculating r, let us try to calculate one thing. Okay, so let us calculate this width. Okay, so let us calculate this width, which is given by r times of sine theta value. Okay, so r times of sine theta value, let us calculate directly. So r times of sine theta at theta is equal to 0. Let us say at theta tends to 0, r sine theta, because you are interested in calculating the width of the body, okay, half width of the Rankine body. So r into sine theta is equal to, r is this expression, m pi minus theta divided by 2u pi sine theta into sine theta is what you have. So now if you see, because we can calculate width directly, so sine theta and sine theta gets cancelled. So in that case, at theta tends to 0, this is limit theta tends to 0, this width, half width, w by 2, half width. If you calculate this half width of the body, if you calculate this half width, w by 2 is equal to limit theta tends to 0, m times of pi minus theta by 2u pi. So if you put theta is equal to 0 here, then definitely this pi and pi gets cancelled. So you have m by 2u is the half width of the body actually here. Yes, radius tends to infinity, correct, because if you put r tends to 0 here, radius tends to infinity, correct, but half width if you calculate, you got m by 2u. So this width is nothing but m by 2u. So if you want to calculate the total width of the body, this is 2 times of this value, which is source strength divided by the uniform velocity. So m by u is the width of the Rankine body. So this is what I want to show you. R tends to infinity, of course, yes, this is true. In all the previous limits we got r tends to infinity, but if you want to calculate the width, which is 2 times of r sine theta, we have calculated half width, which is this value. So I think we have represented this as w is equal to 2 times of r sine theta. Yes, so this is w by 2 we have calculated, which is m by 2u that we have obtained. So means basically when theta is equal to pi, this radius value is m by 2 pi u. When theta is equal to 90, this value is m by 4u, and this half width is basically m by 2u is what we have identified. Clear? So m by 2u is the half width of the body. So the total width of the body is small m divided by u, which is actually here. Okay, so if you see this question now, because for this question you need to understand that, okay, you should have known this theory in order to get this. Okay, it's very simple actually. From stream function we have made the constant value at m is equal to pi m by 2, and we have seen certain analysis. So this is the expression for radius at any location. So depending on this, we have calculated at theta tends to pi, at theta tends to pi by 2, and also at theta tends to 0 we calculated this width, because at theta tends to 0 we know r tends to infinity. So we have calculated this half width, w by 2. Okay, so if you see this w by 2, then we got, if you see this w by 2, now if you see, this forms a Rankine half body. Basically this forms a Rankine half body at this case. Okay, so this forms a Rankine half body. So if this forms a Rankine half body like this, if it forms a Rankine half body like this, then in that case, you know, this width is equal to m by 2u. This width is equal to m by 2u, which means this total width is nothing but m by capital U. Okay, so this is m by capital U. Now they have talked about a source at the origin and a uniform flow at 5 meters per second. So m value is how much? M value is 5 meters per second. A source and the origin at a uniform flow are superimposed. The half body which is formed has a maximum width of 2 meters. Okay, so this half body which is formed has the maximum width of 2 meters. So which means they have given you m by 2u. This value is equal to 2 meters, which means m by u is equal to 4. Okay, so m is given to you already. So u is equal to 5 by 4 meters per second. So the velocity of the uniform flow is 5 by 4 meters per second. They are asking you the width of the body at the origin, means what is this value? The width of the body at origin means this value. So just now we have calculated this at theta is equal to 90. That smaller value is m by 4u. So this is m by 4u. If this is m by 4u, then this total length is m by 2u. We have calculated this length is m by 2 times of u actually. Okay, so m by 2 times of u. So if you simplify this result, we will get m by 2u, correct? So m by 2u is the width of the body at the origin. So m by 2u is m by 2 times of u, which is 5 by 4 actually here. So the value is 2, correct? So this is what you are getting is in meters. So 5 meters per second, uniform flow at 5 meters per second. Okay, sorry. This is u. This is capital U. Then if this is capital 5, then I think these values will change. So let us see. These values will change here slightly. So u is 5 meters per second. So m by u is how much? m by u, they have given the half body which is formed has a maximum width of 2 meters. So m by u is equal to 2 meters, which means m is equal to 10 meter square per second. Okay, so m is equal to 10 is the value. Now they want the width of the body at the origin, m by 2u. So m by 2u is how much now? M by 2u. Let us see. So this is the value. So m by 2u is equal to, m is how much? 10 divided by 2 times of u value. U is 5. So this total cancels out to be 1 meter. So at this location, these points are separated by a distance of 1 meter actually here. Okay, but why this one is coming, you should know. Okay, why these values are m by 4u, m by 2u, m by 2 pi u, why these values are coming is because of this stream function analysis. Clear? Did you all understand how at theta tends to pi, this is the radius, at theta tends to pi by 2, this is the radius, at theta tends to 0, this is width of the half width of the Rankine body, w by 2. Clear? So please type in the chat box, did you all understand this analysis from complex numbers? Actually, if you want to show the same using Cartesian coordinates, it will be very much hectic for you. Okay, because when we are tried to calculate r, this is coming to be infinity, but because practically at theta tends to 0, for a very small angle r value tends to infinity, but r sin theta, this width remains constant after this particular value, m by 2u. Okay, so that's why these bodies are talked as Rankine half bodies actually. Okay, I hope it's clear to you. So whenever you superimpose a doublet and a uniform flow, sorry, a source and a uniform flow with the conditions of Rankine half body, this is how you get the things. Okay, so this is m by 2 pi u, m by 4u, and this is m by 2u. Clear? Okay, so let us solve. I think it's 1-7. Okay, I think there is one more question. Let us see. Yeah, there is one more question, I think. Yes, let us see. The velocity field for a free vertex in the r theta plane is given by radial velocity is equal to v by, sorry, this theta velocity is equal to c by r. Of course, for a vertex, you can see u theta is equal to c by r and u radial is equal to 0. Okay, fine. Along a line of constant theta, of course, along a line of constant theta. So along a line of constant theta is nothing but a radial line. Okay, if c is equal to 0.3, so if c value is given, then the volume flow rate per unit depth between r1 and r2. So see here, what happens generally, the vertex flow happens in this way. Correct? The vertex flow happens in this way. So let us suppose if this is r1 and if this is r2, for example. Okay, now definitely there will be some flow between this. So they are asking you what is the flow actually. Okay, so what they are asking you, what is the flow between these two lines, the flow between these two lines actually here. Okay, so if I want to know the flow between these two lines, can I say if I calculate the equation of this stream function psi is equal to c1, and if I calculate this stream function value psi is equal to c2, the difference between these two stream functions is nothing but the flow per unit depth between these two lines. Can I say this? Yes or no? If I want the discharge, I can say per unit width, of course, psi1 minus psi2, magnitude of this. Can I calculate this value? Yes or no? So please type in the chat box. Can I say this? I can say this. Okay, so that's why if you see this is a vertex, so if I take f dash of z, this is equal to ur minus I times of u theta into e to the power minus I theta. So this is what you have here. Okay, now if you do Milner-Thomson method, replace r with z and theta with 0, then in that case this is e power 0 1. So this implies f dash of z is equal to minus ic by z is what you have. Okay, so if you integrate this, then definitely f of z is nothing but minus I c ln z is what you have here. Okay, so this is minus I c ln z is the case. Okay, u theta is equal to c by r, it's a vertex, ur is 0, f dash of z is equal to 0 minus I times of c by r, I times of u theta into e power minus I theta. So replace here, we got minus ic by z, so minus ic ln z. This is the case. Now if you see carefully, f of z is equal to minus I times of constant, this constant value is anyhow given somewhere, so I times of constant into ln root of x square plus y square plus I times of tan inverse y by x. This is what you have for the logarithm expansion. So if you see the real part and imaginary part, the real part is nothing but I into I minus 1, there is a minus n, so c times of tan inverse y by x. Okay, so this is c times of tan inverse y by x plus, okay, plus I times of minus c into ln root of x square plus y square. So this is the stream function value. So this is the velocity potential function and this is the stream function psi in terms of x comma y. So if this is in terms of x comma y, if you write in terms of polar coordinates, then you know psi of r comma theta is nothing but this root of x square plus y square can be written as r. So minus c ln r is what you have. Okay, so if you want the flow rate, now if you want the flow rate, what you should do? If you want the flow rate, this flow rate is equal to psi at location 1 minus psi at location 2 at radial location 2. So magnitude of this. So psi at location 1 is nothing but minus c ln r1 minus c minus of minus c plus c ln r2. So if you take this c times of ln r2 by r1, this is the discharge because this is the difference in the stream functions. So magnitude of c, what is the value of c they have given you? C value 0.3 meter square per second. So 0.3 times of ln r2 by r1. So what is r2 value? So it is given 0.24 and this is 0.2. 0.24 divided by 0.2. So if you calculate this, you will get the answer in meter cube per second. Okay, for unit width of course. So meter square per second sometimes you write. So if you calculate this expression, ln 0.24 by 0.2, 0.24 by 0.2, logarithm of this into 0.3. So 0.05469, 0.05469 meter cube per second is the discharge that is flowing through this. So we can calculate via Euler equation perpendicular to streamline. Yeah, basically if you take any perpendicular to streamline equation also, but normally Euler's equation can be applied at any point in the flow. Okay, because it's an ideal flow, no viscosity, so you can generally apply that. Okay. Clear? You can integrate actually. If you can take small discharge, you know u theta is equal to c by r. So c by r into the perpendicular distance. If you take basically so at some distance, you see this is dr and 1 unit thickness. Okay, so you can integrate. You will again get the same function. Okay. Look, for example, u theta is like this. Now these two are perpendicular. So if you see u theta into dr into 1 within the limits r1 to r2. If you do this normal integration, you know c is a constant, so dr by r from r1 to r2, which is nothing but c times of log r, so log r2 by r1, r2 by r1, that's what you will get, same thing. Okay, so here also you have calculated c times ln r2 by r1, which is same expression as per this also, but as this is potential flows, I thought of explaining you this way. That's it. Clear? If you can apply normal continuity equation and you can get this if you want. Okay, both are same, both gives you same answer. Clear? Okay, fine. So please type in the chat box, is this clear to all of you? Okay, so since this is a short, for example for some 2 hours, so I have made many points limited here. So please take one class regarding Navier-Stokes equation problems. Okay, I'll try to take, definitely I'll ask you, I'll ask the team and I'll take at some phase slot. Okay, definitely. What are the topics you want? Please tell me, because I understand this is just an Abhyas course. I have given you some very simple in sense, not in terms of quality, but we have restricted the content to so much actually. Okay, because of the time constraint and all, so we have just put our focus on some questions. So please explain ln z expansion. Yeah, I'll explain you. We'll take some time. Okay, I think we have this. Okay, we have some empty slide here. I'll use this chance to explain you ln z expansion. Okay, so see, log z can be written as log x plus iy. Normally you don't know that, so z can be written as r into e power I theta. Correct? So log a into b can be written as log a plus log b. So ln small r is nothing but root of x square plus y square for a complex number x plus iy plus ln e power I theta. So you know this property, this can be written as ln x square plus y square whole power 1 by 2 plus ln e power I theta. So here you have this property that ln x power a, for example, x power n, you can write this as n times of ln x. Okay, so now if you replace this, we have half times of ln x square plus y square plus I theta into ln e. Okay, so this ln of e is nothing but 1, so this value is 1, so this is half times ln x square plus y square plus I times of theta is nothing but tan inverse of y by x. Okay, so this is what you have for the log z expression when z is equal to x plus iy. Okay, so this is how you calculate the values. So this will again give you some complex number, but you can calculate this value using calculator. This value can also be used calculated using calculator. Okay, so that's how. Got it? Okay, Punnab. So basically, if you see, this is a very good lecture actually today, because normally if you search all the Indian other books or even some standard books, if you search, you will find the lengthy expressions. Okay, but using complex numbers, we can make things very short in case of potential flows. Okay, but since this is a very short 2 hours video on some problems practice, I have talked about Rankine body and all. If there could be some time, I would have talked about circulation, flow past a rotating cylinder, all these things also. But yeah, we can look at it some other time. Okay, and hopefully since crash course got started today morning by Amit Dikshit sir, he is also on very fantastic faculty with All India rank 1. So you can just go for some of his definitely his videos would definitely help you out in fluid mechanics. Okay, and he teaches, he also teaches you fluid mechanics at very great level. Okay, so it is very difficult to understand standard books. Yeah, of course many direct things are written, but definitely yes, in Telegram group you can always put your doubts and you can get them solved by us or by SMEs or by your own friends sometimes. Okay, so I hope you enjoyed this fluid mechanics series. In Abhyas, we have solved some really good questions in between in buoyancy and flotation, kinematics. Okay, in vortex flows we have solved. Okay, so definitely tomorrow's class, please don't miss the session, because if you see, we are going to cover questions from all the chapters. Okay, so tomorrow is like cumulative basic revision of all these things. So tomorrow is the last lecture for this Abhyas on fluid mechanics. So we will try to solve the questions on all the chapters. Some 10 chapters I think we have kept, so we'll pick some good questions and we will try to solve them. Okay, so is this clear to all of you, this complex numbers? Okay, this method, if you see, such a fantastic method, we can get the steam function value within just 1-2 things. So please make strategy XCFM. Yeah, I'll make sometime. Okay, maybe we'll find in we need today evening we have a live. I actually have some session on Gate Wallah main channel, so you can attend live there, and I'll help you out how to do something good in interviews. And also in next 2-3 days, if I find some time, definitely I'll make this session on strategy for XCFM. Yeah, I'll make that. Okay, clear? So fine. Then if it's fine, we shall close this session. And yes, so thank you all. We'll meet again tomorrow at 11 a.m. right? Yes, 11 a.m. We'll meet at 11 a.m. and we will work out some more questions. Okay, fine. So I hope it's clear. If you have any doubts, you can ask me, or if you find some topics, if you want anything, you can ask me. Tomorrow is going to be the last session for this Abhyas, so don't miss the session. Okay, we'll solve some good questions. Okay, and definitely if you can solve all these questions what we have solved in Abhyas, you will definitely have the skills for solving all the questions that comes in GATE examination. Okay, fine then. So thank you all. We'll meet tomorrow at 11 a.m. Okay, thank you all. Bye.